Today we are going to be finding the centroid of an area between two different functions. I will also be focusing on how to derive the formula of centroids based on area. So, what is a centroid? Given any geometric figure, we can ask for its centroid, which is the average of the points enclosed by the figure. So how can we use this knowledge to solve this problem? Find coordinates for the centroid of the circular sector formed by the unit circle, the y-axis, and the line y equals x. So considering this shape, the centroid is usually denoted by the coordinates x bar, y bar. Let's start with y bar. So let's imagine that a large number m of points has been scattered uniformly throughout the region. The task confronting us is to add up all of their y coordinates and then divide by m. So it is convenient to divide the region into many thin vertical strips, each of width delta x. And we know that it has to be delta x because no matter which two x values we are choosing the strip between, and no matter how close these two x values are to each other, the width will always be the difference between them, so delta x. And as for the height would simply be the difference in the two y values. The first y value, which is the greater one, minus the second y value, which is the smaller one of the line y equals x. And we're doing this all to determine the amount of points that could be on this rectangle. So to find the proportion of the points that could be lying in this small area, we simply divide the area we found by the total area of the sector and multiply by the number of points total. So m. Now we know roughly the proportion of points that lie on this one sliver of area. Now here's where the idea of the weighted average comes in. Now that we know the proportion of points, we want to find out how much it contributes to the total sum. We can do this by multiplying the proportion by the average value of points, which would be simply y1 plus y2 divided by 2. We can think of the average y value of points on this rectangle to be the weight that the coordinates of all of these points hold in comparison to every single point that lies on the sector. So by multiplying the average y value of points with the proportion, we get the total contribution this rectangle has to the sum. So now if we split the sector up into many of these little rectangles and we add each of their contributions together to form a total sum, then divide by the amount of points, that would be the weighted average of the y value of all points. As you can see, the m cancels out. We can then express this as a Riemann sum. But Riemann sums take a lot of time to evaluate, given that you have to calculate every single term and add them all together. So an easier way to do this would be to do an integral, which would look something like this. So now for the solving. Knowing these two functions, we have the unit circle, which can be represented by the circle equation of radius 1, x squared plus y squared equals 1. If we try to solve for y, we would get square root of 1 minus x squared. And our second function is a simple line, y equals x. So that y value would just simply be x. Recalling the area formula we derived earlier, we can plug that into the integral. And substituting our y values into the integral, we can have this. Now to solve for the total area, it is simply the area of the unit circle sector. So we don't have to do any crazy integrals or anything. We can simply solve for the area of the unit circle, and knowing that the line y equals x creates a 45-degree angle with the y-axis, all we need to do is divide the total circle's area by 8, because 8 times 45 is 360 degrees. So the area of this sector would be pi over 8. Now that we know the area, let's get our bounds. The bounds would simply just be the intersection of the unit circle formula with the line y equals x, but only in quadrant 1. So if we set the equations equal to each other, x equals square root of 1 minus x squared, we would get an answer of 0 and square root of 2 over 2. We also know this because when it's 45 degrees, the x value must be square root of 2 over 2. So now plugging in our bounds and the total area, we get this. And we can solve this by plugging into a calculator, since we understand the concepts behind getting the formula. After plugging it in, we get an answer of 0.6002. Now for the x bar. Going back to the earlier diagram we had, the area would stay the same. But now, instead of focusing on the average y value, we're going to be using the average x value to represent the weight of each x value these points have in comparison to all the possible x values of the points that lie in the sector. Because the width of the strip is so thin, we've already made the assumption that all of these points that lie on the strip have the same x value. And so that would just be the average x value of all our points, x. So the contribution of the x values of the points on this rectangle would simply just be x times the area over the total area multiplied by the number of points total, m. Now if we reimagine all the other thin vertical strips that run along the sector and we add up each of their contributions, we get a sum. Then if we divide that sum by the total number of points, we get the rated average of the x value of all these points. And again, the m's cancel out. Now, like before, we can express this as a Riemann sum from n equals a to b of n times the area over the total area, or we could convert it into the integral. Now this integral will look very similar to the one with the y value, but instead of the average y value, we get the average x value. And knowing our y1 and our y2, we can simply plug it in to the formula, and this is what we get. And given that our a and our b is still the same, and our total area also stays the same, we can plug those values in and compute our integral, giving us an x bar of 0.2486. So, answering the problem, find the coordinates for the centroid of the circular sector formed by the unit circle, the x-axis, and the line y equals x, we get a final answer of 0.6002, 0.2486. Thank you. I hope this was helpful.